Good evening, everyone. Once again, I welcome you all today's evening for the second session of Quantum AI. And I would request all of you to kindly inform your teammates, your friends, so that they can also come and join in. Meanwhile, those who have joined and those who are live, I would request you to quickly share whatever you had revised or whatever last discussion we had. So, those who have joined, I would request you that you can share this message with others also. And at the same time, you can put in the chat what all concepts did we cover in the last session. Yes, hello everyone. So I can see that people are joining in, and we'll wait for a few minutes so that everyone can join in and everyone can take the benefit of it. And as I said, that those who were present in the last session, so I welcome everyone, and I would request that you can quickly share this particular session to link with everyone, those who can get benefited from this particular session. Also, you can write us some feedbacks in the comment box. And by any chance, if you have not joined the Google Classroom, I would request all of you, you all must have got a message, and the message is having one Google Classroom link as well. Because we'll be having notes shared from now onwards, and we'll be having some quizzes, some activities posted on the classroom so that you can assess what we have been discussing in these particular sessions, and that is going to help you to evaluate yourself. So I would request that all of you, as I said, can share with your friends. And let me just quickly check the chat. Yes, good evening, hello. All right. So we also have all the links present in the description as well. So if you can quickly check the description of this particular live link, so you can see that in the description we have the last session link also. Then after that we have the registration link. So registration link is important for getting the certificate. Our team will help you to get added in the portal. And then we have access classroom. So you can see the description. We have one option, access the classroom. So if you click on it, you will be a part of that classroom and you'll start getting all the messages, all the documents in that classroom itself. All right, so it's high time we should start and continue with our discussion. So last time, I'm looking at the chats actually. So I wanted some inputs from you all that what all did we cover in the last session. So can we have a quick input from everyone? Yes, all of you have said hello. So yes, hello to everyone. Good evening to everyone. So let us quickly have some things. Let me ask, do we understand what is quantum computing? You can write yes or no, and we'll start from there only. Okay. So because we left from there, so we'll start from there only. So let us have a bit of discussion by the time all other people are joining in. Let's say you toss a coin. When you are tossing a coin, what is the possibility you will get? And how many possibilities are there if you toss a coin? Just try it and let me know in the comment box. So we have a coin, let's say, and if I toss a coin, so after tossing the coin, what is the possibilities and how many possibilities are there? So there are two possibilities. Possibility number one is either we can get heads or we can get tails. Two possibilities are there. And if we are tossing a coin, after tossing the coin, we are going to get one out of it. Now, if you create a program and by creating a program, you feed it into your computer and then you ask your computer to toss a coin and give an output to you. So, what will be the output? What will be the output from the computer? Same output exactly. Yes, it will be same output. It will be either heads or either tails. So this is how our classical computers behave. The classical computers, they either give heads or give tails. Let us assume that the heads is termed as 0 and tails is termed as 1. So we will have 0, 1 or 1, 0 or 0, 1. This will be a continued thing. We'll continuously get these things only. So this is the outcome we will get from the classical computer. Now, if I ask you, if you do the same operation, if you do the same operation in a quantum computer, what is going to happen? If you do the same operation in the quantum computer, what is going to happen in that particular case? You can write it down in the chat box and let me know. In case of quantum computers, what is going to happen? So quantum computers are complex machines. And these machines, if you see, they work on the principle of quantum physics. We have been discussing the concepts of quantum physics in the last session. And we had discussed something which is called as superposition and something which is called as entanglement. So these two things we had discussed last time. So what do you think? What is going to happen if we are going to ask quantum computer to toss a coin? What is going to be the output? Just think and let me know. Just think and let me know. Okay. So when this is going to happen, when this is going to happen with a quantum computer, things are going to get changed. And I'll explain you like how the things will get changed. So in the classroom also I'm putting the joining link so that everybody gets to know about it. So I have posted in the classroom also. Okay. And let me share my screen. All right. So as we were discussing that we are trying to toss a coin. And when we are trying to toss a coin, at that point of time, it is going to be either head or it is going to be tail, head or tail. So out of two only, there is going to be one option. Just a second. Okay. Okay, fine. Yes. So the kind of output we are going to get is heads would be something like 0, 1 or 1, 0. This is the kind of output we are going to get. But if we do the same thing with a quantum computer, so what is going to happen? In that particular case, in case of a quantum computer, we have the same possibility like heads and tail. That's a possibility, but quantum computer gives one more possibility, and that possibility is that some portion of the output will be 0 and some portion of the output will be 1. That means some portion will tell it is heads and some portion is going to tell that it is tails. So this is a kind of possibility we have in case of quantum computers. And now let us understand the fundamentals. It is very similar that you have a glass of water, you have a lemon, and what you try to do is you try to put very little, a bit of, lemon into the water. Can you deny that water is not having lemon? Can you deny? We cannot deny, right? So if you are putting lemon on what in the water, let it be a single drop of lemon entered into the glass of water. But still, we will say that it is having majorly water, but there's a bit portion, a little portion of lemon is also there inside the water. I hope this example makes it very clear that how this is not only water. This is mostly water, but a bit of lemon content also into it. If we do the vice versa, if we have all the lemon juice only extracted and we put few drops of water, so we will say that, yeah, it is lemon juice, but at the same time, it is not only lemon, it has got few drops of water also. So this is how at the same time it is having two states, a portion of one state and a portion of the other state as well. So it has got two states at the same time. So this is what is a concept which shows superposition. This is what is called as superposition. Schrodinger, he did an experiment with a cat, and there this was a thought experiment, and this experiment said that the cat is live, the cat is dead. And superposition says that at the same time cat is a bit live and it is a bit dead. So at the same time cat can remain in two situations. All right. So now let us try to understand about bits and qubits, superposition, entanglement. So we'll try to understand these parts because these make the fundamentals of quantum computing. Okay, and let me just share from here. I can share the whiteboard. I hope my whiteboard is visible to all. Okay, so let us try to understand now. Okay, so have you all heard about something which is called as logic gates? Logic gates. I think those who have read mathematics, those who have been a student of physics also, and even chemistry, those who have done maybe graduation in science, even IT, computer engineers. So all of these people are having something called as logic gates. So you can always, say yes or no when you are, uh, when you want to express something, and when I'm asking a question. So logic gates. Now, how to represent a logic gate? Let me represent it. So, for example, let me take some other color from here. Yeah, no problem. So let's say this is a logic gate. Okay, so this is a logic gate. Okay. So can you please confirm the link which you have got in the message? Is that link working? You can say yes, the link of the message is working. So you all must have got a WhatsApp message. So if you can quickly let me know if that link is working. Okay, because many people are not basically able to join, I think. So quickly, if you can tell me, you are able to join with the same link which we have shared through the message. So Vijaya says yes. Okay. Okay, fine, fine. So then it is fine. If you have got it from, if you are able to join that way, it's great. Okay, okay. All right. So let me continue and let me explain. So I was explaining that let's say we have, let me take up a shape and I can take up a shape from here. Okay, yes. So here you can see. So this is a logic gate. Now, how does a logic gate behaves? So logic gate takes an input and it gives an output. So I will take one arrow which shows direction also. So it is taking an input and it is going to give an output. So this is how a logic gate behaves. And what could be the input to the logic gate? The input, let me have the input over here. So here we have input and this side we have output. Okay, so one side we have input and other side we have output. So we will get some input, let's say 0 may be the input, 1 may be the input, some input we will get, and we will get one output. Let's say 1 is the output. This is what is called as a logic gate. Now you might be thinking, those who are listening for the first time, those who are hearing for the first time, you might be thinking that what is the purpose of this logic gate? Like what is going to happen with it? Right? What will happen? So I'll tell you. So let's say you want to make a decision and the decision is either yes or no. So the logic gate can help us to bring either of the values 0 or 1. Let's say 0 represents no and 1 represents yes. So is it possible to utilize a logic gate and do decision making? Is it possible? You can say yes or no. So the answer is yes, it is very much possible. So logic gates can be used in decision making. Now understand, if you have a software, you have a program, and inside that program you have a condition, and with the help of that condition, you want to turn a variable's value to 0 or 1. Or many a times we make use of flags. We have flags, right? Flag variables are there. So again, if you want to make the flag variable value as 0 or 1, you may would like to make it in order to represent the state of the system. So at that particular time, these logic gates can help you. You can tell me in the comment box if you are able to understand what exactly is a logic gate. You can tell me in the comment box. If you are able to understand, you can write same page, SP or same page you can write. And now I'm moving towards that more into logic gates we will go and understand. So they are made up of diodes or you can say transistors. So logic gates are made up of diodes or transistors. I'm still waiting for a response. If you are able to understand, you can say yes, you are able to understand. And if you have any question, you can keep on putting the question. So I have opened the screen and I'm trying to basically, check the screen also so that I can keep on answering. Meanwhile, I'll request my team also to request other technical members to basically share this message in the respective groups because I see that it is not being shared. So I'll just request you can help them. They can basically share it. All right. Thanks a lot, Vijaya, for confirming. Now let me clear the screen and yes, it's almost clean. The Zoom has also, it keeps on evolving, it keeps on changing the kind of interface it is having, and I'm also exploring the new interface it is having for the whiteboard. Now let us try to understand that what all types of different types of logic gates do we have. So types of logic gates. You can also mention here in the comment box if you have idea. You can mention over here that what are the types of different logic gates do we have. So we have AND, OR, NOT, NAND, XOR, XNOR, and NOR. So let me just write them here. I'm just writing them here. So we have, yes, exactly. Yes, you are writing it correctly. So Yes. Correct, correct. Yeah. So let me just list them here. So we have and, then we have or, then we have not, then we have next is NAND, NAND, NAND. Then next we have X or, then we have XOR is done, then XNOR, and then we have NOR. Okay. Yes. So not or, yes, yes. So these are the different types of logic gates we have. Okay. And let's have a quick revision. And those who are new, yes, afresh, you are exploring these things. So let's start with the AND. So how do we represent it? Let me show you how do we represent the AND one. So here, let's have, yes. So first we are, yeah. Hmm. And okay. So in case of and, it is represented in this particular manner. You can have it, yeah, like this, and like this, and this way, and this way. So a bit of drawing may not be so good, so just bear with that. And then we will have it like this. So this is the representation of AND gate. And here we have input. This is A and this is B. Okay, B. Okay, this way. And here the output is, here we will write the output as Y is equal to A dot B. Okay, so this is how we'll be writing the output. Now, in this particular case, we have a concept of truth table. Now, this truth table, if you see that whenever we listen to this, I listen to this particular word specifically, when I was initially studying these things. So I was very much, having this in mind. Why do we call it as a truth table? Okay, but let us try to understand what exactly this truth table does. Okay, so this truth table is, it's like this. So this truth table is like this. Okay. So here we have A value, here we have B value, and then here we have output. Okay. So I think this smart pen is not very, it is becoming so smart. So let me have a normal pen. Yes. So this way. So A, B, and output. And now, uh, yes, with a different color, let's have the different color. Okay. So here if we have 0, okay, if the value of A is 0, okay, and the value of B is 0, then in this particular case, the output is also going to be 0. The value of A is 0, the value of B is 1. Here also the output is going to be 0. The value of A is 1, and the value of B is, let's say, 0. In this case, the output is going to be 0. The value of A is 1 and the value of B is 1. In this case only, the value is going to be 1. Okay. So this is what happens in AND, right? This is what happens in AND. Now, if we explore this further, then what is going to happen? Let's say this is the representation of AND. Okay. And now let me represent the OR gate. Control Z. Control Z. Hmm. So how OR gate is basically? uh, getting created, OR gate. So in case of a OR gate, if you see, OR gate will be represented like whether we have 0 or whether we have 1. In that particular case, it is only going to get, let's say if we have, yeah, so here now OR gate. In case of a OR gate, if you have input A, if you have input B, if A is 0, B is 0, the output is also going to be 0. But if you have A as 1, B as 0, the output is going to be 1. The A is 0, B is 1, output is 1. A is 1, B is 1, output is again 1. So here in this case, if you see what is happening, like whenever we have both of them, like both of A and B as 0, in that case only the output is going to get 0. Otherwise, in all the cases, whenever we have at least 1, the output is going to be 1 only. So this is OR condition. If you do any kind of programming, then also you use this OR condition where these logic gates help us to make a decision. Now you must be thinking that if we have something like not two inputs, but if we have more than two inputs, then what is going to happen? Let's say if we have three inputs. So in case of three inputs also, let's say we are talking about and we have input A, B and C. Input A is 0, this is 0, this is 0. Output is also going to be 0. This is 1, this is 0, this is 0. Output is still 0. This is 1, this is 1, this is 0. Output is still 0. This is 1, this is 1, this is 1. Output is now 1. Are you getting? Like in case of AND, it has to be, all of them needs to be 1 only. Then only the output is going to be 1. Otherwise, it is going to get 0. But in case of OR, we need to have at least one, okay, at least one as 1 and rest of the others can be 0. Okay, at least one we require as 1. So let us move ahead. Let me clear the screen. And yes. So OR gate, if you represent, in case of a OR, we represent the formula as, let's say if we have, sorry, control Z. Yes, if we have A and B as input, and we have OR gate. Okay, so OR gate is represented like this. This is A and this is B, and we can represent OR gate like this. Okay, so one input from here, another input from here, and then output is going to. So Y is equal to, we'll represent it as A plus B. Okay, so what operator we are using? We are using an operator which is plus operator. So A and B are input. In OR gate, we are going to get A plus B. In case of AND gate, what was the output? In case of AND gate, the output was A dot B. So 1 dot 0, dot means multiply it. So if you multiply, the output is going to get 0 only. But in case of plus, at least it should be 1. So if it is 1, it is going to get 1 only. Okay. Now, next one is NOT gate. So in case of a NOT gate, so NOT. Okay. So what will happen in NOT gate? NOT gate is very simple. For example, like small kids. Let's say we have small kid and you ask the kid, small kid, okay, go and study. So if you ask a small kid to go and study, what the small kid is going to say? If the small kid is having not mentality. So if the small kid is having not mentality, small kid will give you a response, no, I will play. But if you would have said something else, let's say you have told the small kid, okay, not to go and study, but go and you are telling the kid to go and play. And because the kid is having this not symptom, so the kid is going to say, no, I will, okay, study. So the kid is going to say, I will study. So this is the behavior of NOT gate. Okay. So how this is represented? This is represented like this. You can have a triangle kind of thing here. Just have this here, and here you can have a circle, and this is up. Your input is A and your output is A dash. Okay. So your Y is equal to just A dash. So input is 0, output is going to be 1, input is 1, output is going to be 0. This is what is NOT gate. Okay. Now we have seen now this particular diagram is called as circuit diagram. If you see this particular diagram, what do we call it as? This is called as circuit diagram. So let me write it over here. So CIRCUIT circuit diagram, DIAGRAM, circuit diagram. We call it as circuit diagram. Okay. So now we are trying to understand the gates, which are called as logic gates, and their truth table. So this is truth table. So here, this particular thing is truth table. Okay. What is input and what is output? That is the truth table. So we are seeing the truth table, and we are also seeing the mathematical equation, how it is formed, and we are also seeing the circuit diagram. So these are just technical terminologies, and sometimes they annoy us because we are very new to it. So this is NOT gate, and NOT gate is also important. For example, let's say if the battery is overheated, then shut down the connection, close the connection, disconnect it. So what is happening? So overheat, disconnected. Okay. So sometimes we need to have NOT gate also. Now we understood AND gate, but when we basically try to have your AND gate along with your NOT gate, so your AND gate and along with your NOT gate, then what is happening? So and NOT, it actually becomes NAND. If you see, N means NOT plus. Okay, so in this particular case, if I want to draw a truth table, so I'm not drawing table again and again, I'm just drawing the values over here. So if I want to draw the truth table, what is going to happen? So truth table will be something like this. We have A input, we have B input, A input is 0 and B input is 0. So the output always comes as 0 only in case of AND. Okay, in case of AND. But in case of NAND, okay, in case of NAND, what is going to happen? So after the output, a NOT is going to get applied, and NOT will transform 0 to 1. Similar way, if we have here, let's say, so here we have, yeah, 1, and here we have 0, the output is 0. But because there is a NOT, this again becomes 1. So here if we have 0, here we have 1, the output is 0. But because of NOT, the output gets transformed to again 1. And then here we have 1, here we have 1, output is 1, but here in this case the output becomes 0. So exactly opposite the truth table, if you see the output in case of NAND is exactly opposite of AND. Okay, opposite of AND. This is what happens in case of NAND gate. Now let us move ahead, and now we are moving towards XOR. So XOR, fine. So X basically represents here exclusive. So if you see the meaning of X over here is exclusive. X means EXCLUSIVE, exclusive. Okay. So in case of exclusive, what will happen? In case of exclusive, we will have truth table something like this. We will have A input, we will have B input, then here 0 0. Now first let's say we have OR. So the output of OR would be 0 0 0, 1 0 1, and 1 1, sorry, 0 1 1, and then 1 1 also 1. Okay. Now if we have exclusive XOR, so in case of XOR, what is going to happen? In case of XOR, it is going to be exclusive. So wherever we have 0 0, okay, so wherever we have 0 0, that we will consider, and where we have 1 1, that we will consider. So this is exclusive and this is exclusive. Okay. So where we have 0, 0 that we consider, and where we have 1, 1 that we consider, and we basically make it as 0, and we make it as 0. And now these two, 1, 0 and 0, 1, they remain 1. So this is basically called as exclusive or XOR. Okay. But if this is going to be XNOR, the next one is XNOR, right? So if it is going to be XNOR, so you can understand that in case of XNOR, what will happen? There will be a NOT basically applied here, and 0 will become 1. 1 is going to become 0, and 1 is going to become 0, and 0 is going to become 1. So 1, 0, 0, 1, this is how it is going to become. Okay. So 1, 0, 0, it is going to become this way. 1, 0, 0, 1. So you just need to remember the trick as that here we have X, here we have X and N. So you just need to remember these things. Okay. So the basic truth table of OR will be applied, but along with OR you will have N, along with OR you will have X. So that you just need to remember. Okay, that is what you just need to understand. Now, the circuit diagrams. A circuit diagram for, let's draw it for XOR. Okay. So in case of XOR, we have OR, sorry, control Z, control Z. So if you see, the OR is like this. Let's see, okay, choose the pen. Yes. So the OR is like this. So in OR, we will have this exclusive X. This basically will be X. Okay. Now input will go to this and output will come from here. Now in case of XNOR, so this is OR and it is XOR, but it is XNOR as well. So N will come here, not. So inputs are here and output is here. So how to draw also, that you can understand that how can we draw it. So first we are drawing the OR part. Then in XOR, we are drawing the X part. Then in this particular case, we are drawing the OR part, then N, the NOT part, then X, the X part. So this is what we are trying to do. Okay. So these are the OR, XOR, and we have the XNOR gate also. Now moving further, we have only the last one remaining. So let us understand that also. That is NOR gate. So can you understand how the NOR gate will get created? The NOR one. So let's have it here. The NOR. So if you see, in case of a NOR, we have an OR. So here if you see that we have an OR over here. So let me draw it here. Yeah, an OR. But we have not attached to it this way. So we just need to understand. So whatever is the output, there will be output of OR, there will be a not attached to it. Okay. So for this particular output, not attached to it. So OR's output, first one is 0, so it will become 1. Second one is 1, it will become 0, it will become 0, it will become 0. So it is exactly opposite of what is our OR. Are we clear till this point of time? You can quickly say yes, no, something. But if you have questions, this is very basic. This is something fundamental you must have studied. But I thought before we enter into the qubit part, we should understand these particular things, and it is important. Okay. So these are the logic gates and they work into classical computers. So we need to understand that these are the logic gates and these logic gates, they work into classical computers. Okay. Now let me clear all. Yes, thanks a lot. Clear all the drawings. And now let us come to the quantum gates also. Okay. So quantum gates. Quantum gates. Now, in case of quantum gates, how will it happen? So in case of quantum gates, it is going to be like this. Like we have bits, so we can rename them. So bits are going to become qubits. Okay, so they'll not remain bits, qubits. So what does that particular, what is the meaning? It's just a quantum bit. Like somehow you'll have to represent, no? So if you have bits in classical computers and you want to represent them in case of quantum computers, so you can represent them as qubits, quantum bits. So that is how the name is given. So don't get confused with the names also. It's qubit, quantum bits. Now, moving ahead, we can have a single qubit. We can have a 2 qubit gates. Okay, so single qubit gate, and we have 2 qubits, or we can have three or multiple. Okay, three or multiple qubit gates. So this is how we can have, okay, single qubit, 2 qubit, or multiple qubit gates we can have. Now, let's try to understand with some application. And I think the application could be quantum machine learning. That is what we had actually proposed. So QUANTUM, quantum machine learning. So in case of quantum machine learning, what exactly do we need? We need some algorithm. Now, anyone who is not from machine learning, IT or that background, don't afraid. I'll explain in very, very, very simplistic manner. Okay, so you don't need to afraid or think that now it is going to get bouncer. No, nothing is going to get bouncer. I'll explain it in very layman's term, and you have chat. You can keep on asking in the chat. Okay, let me quickly check the chat as well. So yes, okay, yes. Now, if we talk about machine learning will have something called as algorithm. Even if you don't know, then basically I'll tell you what is an algorithm. It is step by step solution to a problem. So those, specifically those who are from non-IT background, non-tech background, so you must be doing some research, and while doing some research, you must be writing some steps to conduct some experiment. So those steps here we will call them as algorithm. Okay. Plural would be algorithms. Okay. So in case of quantum machine learning also, we have algorithms. Okay. Now, next thing. Next thing is machine learning. Okay. So you should understand what is machine learning. So machine learning is a computer. Okay. A computer gets a software or a program which can take input and make decisions, predictions, forecasts depending upon the previous and or current experiences. Okay, and here experiences is equal to data input to the program. Are you getting what I'm saying? So, for example, let's say you are walking and you were able to see that there is a somebody ate the banana, and you can understand whatever chilka is there, he threw it away. Now, would you step on that particular chilka of the banana? The answer is no. So you are making a decision over here. Why you are making a decision? Because you had an experience with you in the past that whenever there is a slippery surface, if you step on that slippery surface, you can slip and you can get injured. You have this experience, and that's why you made a decision. So that experience is nothing but data only for a computer, or for a computer program, that is data. So in case of quantum machine learning, the machine learning is a code, is a software, is a program. Now don't get confused into these three terms. Here for us, these three terms are same thing. They're same thing. They're not two different things. Okay. Or three different things. Software, program, a code. So that particular software or a code takes an input. It learns from that input and creates some rules. And based upon that rule, whenever something new comes in, what happens? Whenever there is something new, so at that particular point of time, it makes a prediction. It gives an output because it has got the past experience, past data. So that is what is machine learning. That machine is able to take up a decision of its own. That is machine learning. Okay. And now quantum. So now we need to understand that this quantum is going to make some difference from classical. In case of classical machine learning, CLASS, classical ML, you will, if you have a binary problem, what is a binary problem? Can you tell me quickly? If you have a binary problem. So binary problem is the output or the outcome of the problem will be binary, 0 or 1. So this is the binary problem. Example, buy or not buy. So it's a binary decision, no? Buy or not buy. Then on or off. It's a binary decision. So yes or no. So there's so many examples of binary problems. In case of classical machine learning, the output is either going to be 0 or going to be 1. Output cannot be a part of 0 or a part of 1. In case of quantum, it can be. Quantum, the output is going to be some part is 0 and some is 1. This is what is quantum. Can you tell me if you are able to understand? So we try to understand quantum machine learning, the term quantum machine learning. So in machine learning, we have algorithms, and then algorithms are step-by-step solution to a problem. Now, machine learning is a computer code or a program which can take some input, and from those inputs only it can learn, make some rules for itself, and whenever new data will come, it can quickly create a decision based upon the rules it has created. And then what is experiences? Experiences are nothing but data. As a human, we have experiences. As a machine, it has got data only as an input. Now, We understand machine learning, what is quantum and what is classical. So classical can only deal with 0 or 1, but quantum can deal with some part can be 0, some part can be 1. Okay. So let me once again clear the screen now. Okay. Now let us try to understand. We have understood that what is a quantum, what is a classical bit. Okay. Now we need to understand what is a quantum bit as well. What is a quantum bit? So here, classical bit. So in case of a classical bit, the states could be 0 or 1. Two states could be there, 0 or 1. In case of quantum bits, the states, yeah, can you guess what could be the states in case of quantum? Yeah, you can write in the comment. In case of quantum, what can be the states? So we represent them a bit differently. So I'll write it with the help of this pen. Yeah. So we represent them by, let me choose the pen. Okay, yes. This is how we write. Okay. And this is how we write. So this is how we represent. And what is the meaning of it? What is the meaning of this? So in case of classical bits means the computers we use, the whatever programs, whatever softwares we make use of. So that is classical bits. Okay, so here it is the classical bit. But in case of quantum bits, they are represented like this. And why they are represented like this? I'll tell you. The first reason is that they need to be a bit different from the classical bit representation. Okay, so that we can understand these are the quantum bits. And we pronounce them as cat 1, cat 0. Okay, not that cat. So we pronounce this representation as cat 1 and cat 0. This is the representation. Okay. So here we need to understand that these two represent the states. Okay. States means energy states. So let me show you over here. And energy states can be shown something like this. So here we can have this way. And this is one state. This is another state. And this basically you can call it as E1. And this you can call it as E2. And here, this particular thing till this particular thing. Okay. Yes. So this is the difference between E0 and E1. And we call it as delta E. So I hope you understand these notations. So let me write it a little smaller. So delta E, and this delta E is E1 E1 minus E0. Okay. So delta, if you see what is the meaning of delta, that is a small change, a little change. So delta E is a little change. So these are two, basically cat 0 and cat 1 are two representations. And under these two representations, if we try to understand, you can represent two energy states E0 and E1. And there is a delta, there is a change from E0 to E1. If you have energy state E0, that means you are at E0 energy level. And if you go through that delta change, you will reach to E1 energy level. Okay, so that is basically transition from cat 0 to cat 1. Now let me just introduce you with one gate, and this particular gate is called as Pauli gate. So we call it as Pauli, Pauli, Gate gate. So this is Pauli gate, and we call it as Pauli X gate. And how does it represents? So it has got cat1, and then here we have the gate. This is input and this is the gate, and this x is the input, and here we have the output, and the output is 0, cat0. Similar way, when we have cat0 as input and we have the same gate over here, what can be the output? The output is cat1 is the output. So the kind of truth table we will create here, TT, the truth table. So it's simply a table, okay? No confusion, just a table. So if you try to create a truth table here, the truth table would be something like this way. And yes, and the data would be like this. So this is input, this is output. So this is input qubit and this is output qubit. So two qubits are there, input qubit and output qubit. So what will be the input? The same thing you'll have to write. Okay, cat1 and the output qubit will be cat0. Okay, cat0, the output will be cat1. So this is what is the truth table here. This is Pauli's gate. So sometimes what happens, by the representation itself, we get confused. So don't get confused. It's very simple. The way we write 0 and 1, very similar way we are writing cat1 and cat0. So what is cat1? So you have a pipe symbol, you have 1, and then you have a greater than symbol. It's simple, no? So with these symbols, it becomes cat1. And again, the second 0, it becomes cat0. Now, truth table. Truth table is simply a table which basically represents the set of inputs and the kind of gate applied through which the input is passing and the kind of output it will have. That's it. Okay. So this is what is called as Pauli gate. So now we have entered into what is called as quantum computing, and we are trying to understand the quantum bits. So this one is basically Pauli gate, and we have more such gates, and I'll be explaining those things to you because it's almost now 8:12. So we'll be closing up here, and I'll be explaining it to you almost for 2-3 days. So tomorrow also we will have the same thing, same schedule, and if we don't have, then we will announce. Now, important instructions. So point number one. So tomorrow we will have same schedule, 7 to 8 we will have, and we'll begin on time tomorrow. I'm sorry for the delay today. Second thing is that you need to join the classroom. So if you have not joined the classroom, please do that. Third thing is we will be having mostly live sessions. So you can just go to the YouTube channel, that is Indeed Inspiring Infotech. And I think, yes, I can appeal you. You can surely like and subscribe to our videos. That will help us and encourage us. But if you go to the channel, whenever we are live, it shows over there. And if you will subscribe, you'll get the notification also that we are coming live. So we will be coming live only. If needed, we will connect separately. Otherwise, we'll come on YouTube live. Okay. So that is another thing. We will share the link also beforehand, but you can directly come on the YouTube channel and you can get the live from there. Third thing is, if somebody has not done the registration, you should do it, because from there only the team will add you in the portal and will help you to get the certificates also. So these are the requests I'm making to all of you. And I believe it was very simple today. And it is going to be simple only. But yes, upcoming would be more interesting, because these were the classical bits and classical gates. Now we have just entered into the quantum bits and quantum gates. So we will try to understand with the help of these gates, with the help of certain equations, and we'll try to understand with the help of these things, superposition and entanglement. And that is going to really be very interesting. And tomorrow we'll be covering that. Thank you very much. And keep watching, remain with us, keep learning. Have a good day ahead.